Welcome back. Today we're going to talk about conjugated molecules. And we're going to get started by defining what conjugation is all about. If you consider a molecule like the one shown here, you notice that there's a bunch of different double bonds in this molecule. And for the highlighted region right here in red, the one thing to notice is that these two double bonds are separated by an sp3 hybridized carbon. And as a result, in respect to each other, we regard these two alkenes as being isolated. Now, the one on the very left is absolutely isolated. It's not conjugated in any way due to that break, the break due to the sp3 hybridized carbon, which you can see more clearly right here. And the reason why that is a break is because what leads to conjugation is the ability to have multiple p orbitals aligned in respect to each other from carbon to carbon, parallel to each other, and without an interruption, which, needless to say, the moment you have an sp3 hybridized carbon, you are no longer giving that p orbital to that carbon to complete the entire section of a pi system. And one way to kind of think of this is to kind of associate it to a street that ends up having no outlet, which, needless to say, I've done this plenty of times myself. And yeah, it's kind of frustrating because you have to turn around and go back the way you came. But yeah, anyway. Now another type of double bond system that you may encounter is this one right here, where actually the very same carbon here in the middle contains the two double bonds. And although you might think, oh, okay, well, this is perfect because the p orbitals are going to be for sure lined up with each other, in reality, doesn't exactly work that way. Now, this system, we call it a cumulated diene system. And you are basically dealing with something that's, in essence, the same as an isolated alkene. You don't really have any additional stability. And the reason why is because the carbon here in the middle is sp hybridized. And what that ultimately means is that the two p orbitals of the central carbon are orthogonal to each other. So they don't actually overlap with each other and they don't complete a pi system. So it basically looks like an overpass on a freeway, yes, it's there and you might be passing, by it, but you're not on it. And there's no direct way to, get from the lower roads to the upper road in this overpass. Now, on the other hand, if you look at the green highlighted region right here, you'll notice that you have double bond, followed by single bond, followed by double bond, followed by single bond, followed by double bond, pretty much in a sequential manner. This is what we do refer to as a conjugated system. And the main reason why is because we're going to have full overlap of p orbitals. Now, what that also allows us to do is to delocalize electrons throughout much greater surface area within the molecule. So they're not fully localized to those two atoms. They have more of a more ground to cover, so to speak. And as I just mentioned, in this entire system, there is no breaks. All the carbons in question are sp2 hybridized. The last one is sp hybridized only, but it does have the one p orbital that can completely overlap parallelly to the rest of the orbitals. So this is like through and through a full highway by which the electrons can basically move about, and I myself call it the pi way. So this is what conjugation is all about. All right, now if you think about the idea that, okay, you have multiple bonds and the electrons of the pi bonds can delocalize, that also brings up the idea that, okay, so you can definitely move those pi electrons about, such that you could bring the electrons here onto that carbon. So now you have a charge separation, which at first looks pretty terrible. You might say there's no reason for that to happen, right? Because you're violating, well, not exactly violating the outer rule, but you are now dealing with a carbon with only 6 electrons right here. But you get this segment where the positive charge is now next to a double bond, and then that double bond can kind of provide some assistance in terms of helping out this, carbocation. Basically, if the pi bond set of electrons moves towards the carbocation, you'll end up relocating the double bond. Uh, of course, that means that now the carbon that is down here becomes a carbocation, but then that carbocation is next to another double bond. And this system of resonance structure is actually a really good method by which the molecule can stabilize the separation of charges. Um, in essence, the molecule is being able to spread the charges, through a much greater surface area that tends to help out with dissipating potential energy issues that you might have otherwise. So the thing to kind of keep in mind is that because of this conjugation, this resonance structure, you do end up with carbon-carbon bonds that actually share single and double bond characters. And the perfect example is given in this diene molecule, in which the double bond has a value of 1.34 angstroms. Straight out single bonds have a value of 1.53 angstroms, but the bonds where the conjugation happens have a value that's in between a single and double bond, simply because they have a dual character. They have single bond character, they have double bond character. All right, so with that, we'll stop the video right here. And in the next one, we'll talk about addition reactions as they pertain to conjugated systems. So see you in the next one.